All right. Thanks everyone for coming out. Yeah, it's an exciting time, and I'm going to try to tell you about what we're trying to do, and a lot of this is slides that were from the Probe's kickoff meeting from NASA. So these are mostly NASA slides that some of us who are on the instrument side kind of went through a lot before, but I want to make sure that the science team is aware of what we're doing, how the study is made, and what some of the rules are going to be for what we deliver, and how we cost this mission, how we make a mission that will be something that the decadal survey will be receptive to and will not throw out. Remember, our overall goal is to get the decadal survey to recommend this mission as a high priority for the next decade. So NASA's goal in this whole thing is something that they realized from the last decade, is that they wanted to have the decadal survey prioritize some missions that are smaller than the multi-billion-dollar large missions and get those recommended into the portfolio to give them some programmatic flexibility going forward, so that in the next decade, depending on what the budget scenario looks like, they won't be tied into picking only the top thing, like what they're doing this decade with W-FIRST. They'll be able to make a mix of missions that will give them flexibility to match what happens in the next decade. And so the probe class being something bigger than a mid-X, but smaller than a billion, so the 400 to a billion, is something that they wish that they had had in the previous decade. And so in order to make that happen, they're funding these studies for people to develop missions that will be proof of concept that at the probe class you can do really high priority science, and that there are a lot of missions that are executable in that range that are exciting to do. And so they're funding these studies. The study PIs, that's me, is responsible for delivering the final products, which I'll describe. They will then just take these final products, hand them to the Decadal Survey Committee, and then you don't have much control after that. The survey committee will decide to do what they do. Hopefully they will agree that this is a really good mission class to have, and that there's a lot of exciting science that can be done at this class. So they could rank individual probe class mission concepts like STROBE-X first, or they could say, we think the probe class is a good thing to have, and we'll let you decide the prioritization based on the scientific context at the time when these things are starting in 2023 or so. We don't know what they will do. Here are the ones that were selected, just so you've seen them all. NASA has emphasized that we are not in competition. This is not a competition. Everyone is meant to be helpful to each other and work together, and we're all going to be using the same design lab studies, and we'll all be submitting to the decadal survey. It's not a competition. Everyone is going to be submitted. But also it's important to know that several people who didn't get selected are continuing and doing their studies unfunded by NASA headquarters, but using their own money. Like there's a medium energy gamma ray one at Goddard, and there's plenty of others where people will submit. So this is not restricted. These are not the only ones that can submit white papers to the decadal survey. Anyone is welcome to submit to the decadal survey. It's an open call. We just have an advantage in that we're sort of pre-blessed by NASA as one that was selected, and we will get an official funded design lab study at the IDL, which will give us the input that they need for the costing in a way that follows the rules that they expect. So that's really good. For us, it's important to notice that we're not in competition, but TAP, the Transient Astrophysics Probe led by Jordan Camp, has a lot of overlap with it. It's a wide field monitor using a lobster eye telescope. And so that's something I really want the science team to focus on, is what's the relationship here? How well do we do on the science that TAP is planning to do? The lobster eye has a wide field of view, but a tiny amount of effective area in any one direction. I have some notes on comparisons between the wide field monitor and TAP that we can talk about later if anyone wants to. But we want to know clearly how well we will do on EM follow-up science, on gamma ray burst science, high Z gamma ray bursts, so that we can show that, and privately, I hope that they say, oh yeah, the science of EM follow-ups is great, but if you do STROBE-X, you'll get that science and you'll get a lot more. So our point of contact, just to point that, is Gabe Carpati at Goddard is the headquarters kind of point of contact for our study. So he's the one that we talk to whenever we have questions. This may not be readable like that. So our study schedule, we started back in May when we first got funding. Right now we've been having these great science telecons, which I think have been fantastic. Thanks to Tom and the SOC, everyone, for arranging those and for doing the interviews afterwards. The social media presence has been great. So we've been working on laying out different pieces of the science case, developing requirements, and then here we really want to focus even more on science requirements. So we're at the requirements meeting here right now. Then right after this meeting, we start planning for the instrument design run. So several of us who are in the hardware side are going to Goddard on Thursday and Friday this week to talk to the instrument design lab people about the kinds of things that we want them to look into for our instrument study. And so that begins our planning, detailed planning for the instrument study, which will be done at Goddard over a week at the end of November. And so that's where we'll have the full services of the IDL to do our study. We hope then to really clarify what the instruments will be and what their capabilities will be. And then the idea is that sort of going forward from that, we are doing performance simulations, things that will feed directly into what we will present in the paper in the end. Here's what STROBE-X, as envisioned, will do. And we'll be developing the technology roadmap, which thankfully for STROBE-X, a real strength of our mission is that there's not much of a technology roadmap needed. The technologies exist. They've been developed in Europe for LOFT, the detectors and the collimators, been developed for NICER, which is flying now and doing really well. So we don't have any big uncertainties in technology, and we want to make that really clear. So we'll be doing that in our report. There will be, I think we'll have a team meeting at the AAS, and that's where one of our first big public presentations will be in front of everyone at the AAS. I will present there in January. I also presented it for the X-ray Science Special Interest Group at the head meeting in Idaho. That's already been done, and that was actually very well received, I would say, if anyone didn't know that. The head meeting presentation got people really excited. Yeah?
And the AAS will be a special session?
It is. I'll have slides on that in a minute. Yeah, it will be a special session. Then in April, we will do the mission design run, which is where we'll get the whole mission together. That will include the ground system, what our data rates will be, we'll know what launcher it will be, what orbit we'll get to, all that kind of mission architecture stuff. And that will be the final wrap-up of all the hardware definition of the mission. And then from April through the rest of the year until about September, when we finish the report, it'll be writing that report, and I'll describe the format of that. So we'll be delivering our final report, hopefully in September. If it slips late, they'll give us a no-cost extension, but it absolutely cannot be turned in later than December 31st of 2018. So there will be special sessions at the Winter AAS. There's back-to-back ones. One on the large-scale missions, which if you've been following, it includes LYNX, it's the X-ray surveyor, the new name for the X-ray surveyor, and then several other large-scale missions. And then the afternoon session will be ours, the probe class studies. So I'll get 10 minutes only, including questions. So it's going to be a very brief overview, just talking about the progress of our study and what the mission is and letting people know. They don't expect us to have it costed and finalized at that point or anything like that. But they will have a joining poster session, and I absolutely encourage people to present any STROBE-X relevant science in that poster session. So please think about putting in an abstract. The deadline is October 3rd for AAS. Let's get a lot of posters talking about how great STROBE-X will be. I mean, that'd be fantastic. A big part of our job is getting the community excited about STROBE-X as a mission. They should be in their mind, and whenever they think of some science, like, oh, how will STROBE-X do on that? And so let's make sure we publicize that. So the final product will be two big things. The one that this community is worried about is the study report that will outline the science, and then the part that we'll be developing with the IDL and MDL will be the engineering concept definition package. The study, all of that stuff I've already said. the decadal survey will really just get that study. They won't get the big engineering package because they don't want to read that from every single mission. So really our study package, our white paper needs to be self-contained and contain the top level description of everything, and then the engineering package will be the kind of technical backup of it if they want to go to that. And then lastly, the other piece of it that we really have no input in is they take our white paper and our engineering concept package, and they will hand those to an independent cost estimating group, it's probably aerospace, and they will do an independent cost estimate. And that is a critical piece of this puzzle because they need to bless us that we will come in at under $1 billion. If they say there's no way that STROBE-X can be executed in under $1 billion, we'll basically be removed from consideration for a probe class mission because they'll say, look, this can't be done. And there's been a lot of history with people claiming they could do things for cheap and then not being able to do it, and it costs NASA a lot of money and it's very painful. So we want to make sure that we put the inputs into our packages that let them know that that we will make it under $1 billion. And I will show you some, we'll talk more about that. Okay, so as I said, the study report is a complete standalone document. It's important that it's science heavy. The decadal survey cares most about what science will be executed. It's true they need a design that's clear enough to show that at least a proof of concept that there is, or a demonstration that there is a mission that can do this science, but that's not so important because the mission will be developed in the next decade, really. It will start phase A in the next decade. But there has to be a motivating science to why would you want to develop it. So this report will be very science heavy. It will talk about the observations that STROBE-X can do, the science yield that will come out, how that will, work if there is, if D-scopes are needed or anything like that, so that it's kind of this, some parameterization. And then they list basically table of contents for it, which looks a lot like a proposal, but it won't have as much detail on, a management plan and things like that, because that's not where we are. We're at the point of defining the science for the mission, so that's really going to be the focus, and that's the focus for the science team for sure. It cannot be more than 50 pages. They recommend between 20 and 40, so this is not a huge document. We're going to have to be concise. STROBE-X is so flexible. We have so many different types of science we can do. We can easily have pages on each one of these subtopics that we're presenting here. We're going to have to condense it down and make it strong and have to pick really good figures. So great figures that demonstrate the capability that anyone from imagine a random person from the decadal survey flipping through this, they want to get the message that this is really exciting. So that's going to be key, to develop good simulations and good figures. And obviously it will be publicly released. All right, so the engineering concept package, I won't talk too much about it because it's not so much a big concern, but it's basically the big giant stacks of PowerPoints that will come out of the design study. The key is that we may end up with something slightly different. The danger is that you do your study early, this engineering study early, and then you learn things and you figure, and you make a change to the design, and that makes it a little tricky because the design study is supposed to represent exactly what we're proposing in the white paper. And so they have a menu of options for how you deal with that. One is that what we hope happens is that we go in with enough knowledge based on our previous experience with LOFT and NICER that we pretty much have it spec'd out right. The study is done on the mission as we expect, and then the report that they generate from the IDL and MDL is exactly what we want. That's great, and we just send it in. But if we do have to modify something, say we decide we can't meet the specs and we need to de-scope something, change the instrument parameters or whatever, then there's a couple of options. We can either pay our own money out of our study or money from institutions or whatever, to have engineers revisit the parts of the study that need to be changed and then submit the updated engineering study. Or you can just, if you don't have the money for that, they funded us an incredibly low amount, so we don't really have much of any money. But hopefully we can get some internal money from various places. But you can just submit the original one with an erratum written in plain English. It says, look, this study is exactly right except for X, Y, and Z, and you describe what the modifications needed to be so that in enough detail that the cost estimators and the decadal survey can understand what needs to be changed in order to change their cost estimates. So the technology, as I mentioned, so we are not funded at all to develop technology for this. Part of our job will be to list the technologies and give a kind of a roadmap for what technologies need to be developed, but we don't have any money now to develop them. So one of the things we'll probably be talking about later this week is ways that we could parlay this study into technology development funds through things like APRA and whatnot. So maybe we can get, now that we're selected, we can put in an APRA proposal saying, look, this is the, this would help to advance the TRL of the STROBE-X detectors in one way or another, and try to get APRA funding to do that. So we'll be looking at those kind of options. There's these TRL milestones you need to be at by 2023. None of those are a problem for us. We're not worried about TRL development.
The technology gaps, that's a little tricky. I don't know if you can ask about that at all, but I just finished a review of technology gaps. And
you mean for the program annual technical report?
Yeah, exactly. Is that what you're talking about here?
No. This is technology gaps between where we are now and what we would need to be at TRL 6 to execute STROBE-X.
Okay, so you're not
So
beneficial.
those could be things that you would put into the technology gap list.
Right.
But the technology gaps, those are pretty broad. A lot of them. Here, this is more specific technology roadmap for what we need to execute STROBE-X. It might be like, we have to have a collimator that's, TRL 6 by then. Right here we are at TRL 4. Here's what we need to get there. All right, this is just one note that they put in on terminology in case you aren't familiar with all of this, which you might hear more and more as the study goes on. If you have some resource like a power or a mass or a whatever, your engineers tell you that how much you think it's going to be, X number of watts say. That's the current best estimate, CBE, that's an engineering term. If you are early in the design stage of something, that current best estimate is likely to change as you get more and more design maturity. And so there's a maximum value that you think it will have. It has 50 watts now, but because I haven't counted everything exactly, it might grow to 75 watts. That's your contingency that you've levied on that, so that gets you this maximum expected value. And then the amount that you have allocated in your budget above that is your margin. So if you have 100 watts that you know that your power system can generate, you're currently at 50 watts, there's 25 watts maybe for your contingency, and then your margin is the amount above that maximum value. It's how much margin you have left before you get into real trouble. So you might hear those terms, but contingency and margin are useful terms. All right, so now there's a few things that they've stated. This is directly from NASA. These are mandatory rules that we have to follow that set the guidelines for how we define this mission. So these aren't things that we can easily change. If we have any problem with any of them, we need to go to Gabe Carpati, our point of contact, and talk to him about them. But all the decadal probes are Class B, unmodified Class B missions. That's a pretty high reliability ranking for NASA. Class A is things like human spaceflight. Most of the things, if you've done SMEXs and mid-Xs, those can be Class C or Class D. Nicer is modified Class D even. So that levies quite a bit of overhead for safety and mission assurance and configuration control. A lot of management overhead in a Class B mission. A lot of testing, parts selection, all that kind of stuff is affected, and that all costs money. Launch vehicle cost is a really simple situation. Everybody is using 150 million. So we we know that we have cost of the launch vehicle. We cannot use any of the heavies, so we are not allowed to consider the Falcon 9 Heavy or the SLS or anything like that. So we are designing everything for a straight Falcon 9 launch from Cape Canaveral, and we'll talk more about that. Colleen will talk about that in her talk. They have set rules on what the unencumbered cost reserves need to be. And everything is $1 billion in FY18 dollars. So when you're thinking about what time scale to think about for some of your science, what things will be in flight at that time, what we're supposed to use is a start date for Phase A of October 1st, 2023. That's sort of the soonest you can imagine if NASA goes through the decadal survey, probes are highly recommended, STROBE-X is right at the top of the list. They decide that they want to do a probe, that the money is right for it, they put it into Congress, Congress approves it, and the line item starts 2023. So you then wouldn't be able to launch for at least, say, 5 years, so think of STROBE-X as launching in 2028. So they also provide some rules of thumb. These aren't exactly the same as those mandatory rules, but what they expect to see in these kind of costed things, there's percentages that they have based on previous experience for what reserves have to be, what operations might cost, all the management, system engineering, mission assurance for a Class B mission of this scale. So these are difficult for us to turn the dial too much. So they lay this out, and then they end up with, you really have for your spacecraft and payload and things that you're going to do, really only 460 million out of a maximum of $1 billion. So it really starts to get cut down a lot when you count all the management overhead. And also, mass is a significant cost driver because so many of the rules of thumb are based on scalings with mass, and that's a big factor for us. Some other rules of thumb, they talk about how much a spacecraft will cost. They have a rule, some list here of like previous missions like Kepler, and talking about a 500 kilogram payload. We have to watch out there. Our payload is going to be a lot more than 500 kilograms, so be careful. Also, instruments, they claim typically cost 800 to 1,000, 800 to 1 million per kilogram. That's, again, based on certain types of instruments. If we are costed using this, we are dead. We're about a $7 billion mission. So we are going to have to work hard on getting them not to apply that scaling, because that's definitely not appropriate. High energy missions often have this problem that we're more massive and more simple per unit mass than some of the things that might be an optical telescope that requires an enormous amount of detailed calibration and stuff. So they say in the on-axis 1 meter telescope costs $550 million and blah, blah, blah. So why the hell is that?
To remind me tomorrow.
Yeah, okay. I would say, and I think NICER has learned this too, don't call us a telescope. So the XRCA's concentrator units are not telescopes, because people think telescopes are expensive. These are much, much easier to manufacture, to align, to build than a telescope, which needs a fraction of a wavelength, accuracies and all that kind of stuff. So we're working out a cost strategy, and one thing that really helps us is analogies with the Fermi mission. Fermi is demonstrably existing. It's a probe class mission. It costs about 600 million. It has a similar number of electronics channels to STROBE-X. It has a roughly similar mass. So it's a really good proof of concept that someone can't say, look, there's no way you can do this. They did it. They flew 75 square meters of silicon drift detectors with millions of electronics channels with a lot of data processing on board with a high data rate. So if they can do it, 10 years later, we should be able to do it too. I wanted to just show people, go back over to some of these weaknesses from our review. Our review for when we were selected was incredibly strong. They really liked a lot of it. They liked the technology. They liked the broad science. But we should think about some of the weaknesses. One is that they thought we needed to work more to address the broad science, that is gravitational wave, high redshift GRBs, other transients follow-ups. We didn't have that as much in the short proposal because I think we only had 5 pages or something for the science case. Now we have more, and it's really important for us to emphasize, as I already said, that broad community covering the hot topics of today, which is high redshift, which is gravitational wave follow-ups for sure. The other thing we want to do is, we don't know what's going to happen to Lynx or other large missions in the US, but we do know that Athena is going forward. So it's always good to keep in our mind how we relate to Athena, and Athena people like DDA Barre definitely react when we say there's not going to be any other timing capabilities in space at that time. That's not true. Athena has a significant timing capability. They did work hard to get fast timing detectors on Athena. It's definitely not STROBE-X in terms of its flexibility and collecting area and all that. But we just need to keep in mind our relationship with that and how we defend from saying, oh, well, you don't need to do STROBE-X, Athena's going to be there, we'll do everything you want. That's not true, and so we need to make sure that's clear. And there's a question about telemetry limits, which we'll think about on the engineering side. We definitely, high telemetry rate is important. Make sure you're thinking about how important the event-by-event data from the sky monitor is. The sky is very bright when you have a very large field of view, so the telemetry can be driven a lot by the sky monitor telemetry. And so we want to know how important that is to you so that we can fight that fight and get that resource for the mission. All right, so last thought, STROBE-X grew out of LOFT and NICER. But together, it's really just such a strong mission. I think it's super exciting to see over the next few days what we can do. It's got so much more collecting area than NICER, and we're already seeing how great NICER can be. I know maybe many of you haven't seen a lot of the results yet from NICER, so I'm thinking maybe on Friday we'll pull together some of the slides that we had from the head meeting. Maybe Jackie can help with that, and my slides, and Slavko's, and
Oh,
you can see.
we're not due on Wednesday.
Oh, I'm sorry, I meant the last day, Wednesday morning, when there's open time so far. We can maybe schedule a little thing and show some of the results. NICER is doing fantastic, right? Compared to LOFT, which there's been a tremendous amount of study on, the Yellow Book and many, many white papers, you now take that, which is already so capable, and add an extended energy range and much higher energy resolution in the soft band and in the iron line region. So it really brings together so much. And we're really lucky that we're so highly scalable. Because everything is built out of modular units, we can easily de-scope down to a smaller value if the mass is just too high and the scaling laws are making it look like we're going to struggle to get them to approve it and say you can do it in a billion. We can easily scale back. So to help that, we've provided response matrices at several different points, and so we do want people to always be thinking about what would it mean if we had to scale back the effective area by these factors. How bad would that be? Is that you can just observe a little longer or whatever. We want to know what the impacts are so that we know what dials we have to be able to turn. And that's it. Thanks.